Hello and welcome to lecture 13 of computational complexity. In this lecture we will see time hierarchy theorem, and this will be the last topic on the complexity classes based on time, at least for now. Okay, so what is time hierarchy theorem? Okay, so we know that if we give more time to a computer or a Turing machine, right, it can possibly do more, right? So you allow it to compute for longer, then maybe it can do better. However, is there a way to formalize this? So we know that non-determinism also seems to help, right? We said that verification is easier than actually deciding, but then we also know that we still don't know whether P is equal to NP or not. So something seems to be true need not necessarily mean that there is an easy way to show that it is true. But the statement that I just said about if we give a machine more time, can it compute more, right? This particular thing, we will see that it is indeed the case. There are languages that we can compute if we have more time as compared to if we had lesser time, right? So we'll see what these languages are. So more formally, how much of, like, if you have more time, how much more time should you need to give so that there is we can actually compute more, right? So we'll see that, right? This is called time hierarchy theorem, and I'll just formally state it. Right? Let T1 and T2 be so-called time constructible functions, right? So we'll, at the end of the lecture, I will define what is time constructible. So it's a bit of a technical definition, right? Such that T1n log T1n is little o of T2n. Okay, then the time T1n is contained in the time T2n, right? This is what we will expect. So what we are saying here is that T1 has to be little o of T2, and not just T1 has to be little o of T2. We want T1 log T1 to be little o of T2, right? Right. So for instance, let's say T1 is n and T2 is n squared. Okay, T1 is n and T2 is n squared, then n log n is little o of n squared. So that is indeed the case. Or T1 is n squared and T2 is n cubed, right? Even then n squared log n squared, which is n squared log n, it is also little o of n cubed. So that's also fine. But so you need at least this logarithmic separation. That is what we are saying here. In that case, d time of T1n is contained in d time of T2n. This is not very difficult to see, right? Because one is contained inside the other, just because T2 is bigger than T1. That is not so difficult to see. What time hierarchy theorem says that it is strictly contained inside the other. D time T1n is contained in T2n and it is strict. Meaning there are languages in T2n, d time T2n, which are not there in d time T1n. Meaning there are languages that require time T2 to compute, but cannot be computed in or cannot be decided in time T1. Right? So the main idea for this proof is by diagonalization. You may have seen diagonalization in the theory of computation course to show undecidability. However, we will do a very small recap here because the proof of time hierarchy theorem also is along very similar lines. So it will also help as a small warm up to see the diagonalization, right? So what was the undecidable language that we saw that you might have seen? So one of such language is what is called ATM, right? It is actually the acceptance problem. So given M, a Turing machine's the encoding of a Turing machine, and W, which is an input, ATM is a class of all M and W such that M accepts W. So it's simply, the question is, to decide whether M accepts W. So it seems like a very simple thing to do, to decide whether M accepts W, but it turns out to be extremely hard because suppose the computation is ongoing, you don't know how long to let it go. Either M could accept W, M could reject W, or M may just not do either. It may just continue computation, keep continuing computation. So then how do you distinguish, is it just running on a loop, or is it going to stop at some point? How do you know when to stop, right? So we don't know that. That is what makes this challenging. And this problem is undecidable. Given M and W, whether M accepts W or not, it's undecidable, mainly because we don't know to determine whether it halts or not. So sometimes this is also referred to as a halting problem. But there is also another language where M halts on W, even that is undecidable. Okay. But anyway, let's stick to this now in order to not have any confusion. We will stick to ATM, where we have to decide whether given Turing machine M accepts a given string W. Right. So now how do you show that it is undecidable? Right. So like many of these proofs go, we start by contradiction. Okay. Suppose there exists M prime, a Turing machine that decides ATM. Okay, suppose let's say it is decidable, which means it has to have a decider, and we call it M prime. Now let's construct a Turing machine D as follows. So using M prime, now we will construct a Turing machine D, and what does D do? Given an input, so D just takes one input, which is a description of a Turing machine. Okay. So now when I write it like this, M with angular brackets, it means I'm giving D the input M, which is the description of a Turing machine M. Okay. So the angular brackets denote it's a description of a Turing machine. What do? We run M on we run M prime on this. Okay. So what we do is we run M prime on, so M prime is a decider for ATM, which means it is given a string and given a Turing machine and a string, and it's asked to decide whether this string accepts, this Turing machine accepts this string, right? So run M prime, which is a known decider on this, or an assumed decider on this, right? So what is this? M prime is a decider, and this and this are description of the Turing machine M. Okay. So you are giving, so any Turing machine has a description. So you can say list down the number of states, you can list down the alphabet, you can list down all the transitions, right? Like that you can write a description. Okay. Now then, so M prime is a decider, which means it halts on all the inputs. So then what do? You accept if M prime rejects, and you reject if M prime accepts. So it's very simple. You just do, sorry, just give me 1 second. Sorry. So basically what you do is you run the decider of ATM on M and its description, and you do the opposite, right? So this is fine. So far so good. We have a decider for ATM called M prime, and we built another Turing machine using M prime as a subroutine, which is D. So what is the contradiction? Till now there is no contradiction actually. The contradiction happens when you run D on its own input. So D is this Turing machine that we just constructed, and what happens when you run D on its own description, right? So what will happen here? So note that now D will take the place of M, right? So now M prime will be run on D and its description. So then M prime will see whether D accepts D's description. If D accepts D's description, then M prime will accept, in which case there will be a reject over here, right? So if D accepts its own description, then M prime accepts D, right, its own the description of D, then D ends up rejects its own description. So note where we started and where we ended up. If D accepts its own description, then M prime accepts the description of D, but then D does the opposite of what M prime is doing, right? So D will reject then the string. So there is a contradiction. What if the other way? If D rejects its own description, then M prime also rejects its own description, right? But then D will flip the output, flip the result. So then D will accept its own description. So it's a contradiction, obvious contradiction. It may be, this concept may be a bit confusing, especially if you have not seen diagonalization before. What is happening is we are constructing this machine, right? So this is the diagonalization part. This is why it's called diagonalization. So you can read up more if you're interested. So this is the flipping of the output, right? So when you feed D its own description as the input, M prime will reject if it accepts its own description, but then D flips M prime's output. So it ends up doing the opposite of what it is supposed to end up doing. So this is a contradiction here. So this is a contradiction. So this means that contradiction to what? So everything here was a natural consequence of what we did, assuming that there is a machine that decides ATM. So that is the only assumption that we made. So consequently, ATM is undecidable. This assumption was wrong, and hence ATM is undecidable, right? So ATM is undecidable, right? So just to quickly recap, D was to simulate M on its own description, or rather we ran M prime on M and its own description, and then we flipped the output. So when this M is replaced, this M and M, the description of M, the part that I am circling in green, when this is replaced by D and its own description, then we go to a contradiction, right? So let's now try to see what is the time hierarchy theorem. So time hierarchy theorem follows pretty much the same proof, except that we will bring in a time factor into the into this whole thing. So it will also follow diagonalization. It will also follow pretty much the same theme, except that we will also start looking at the time, and we'll show a contradiction, right? So once again, statement of time hierarchy theorem: if T1, T2 are time constructible functions such that T1 log T1 is lid low of T2, then d time T1 is contained in d time T2, which is not that difficult to see, but it is strictly contained, meaning there are some languages that are in d time T2 but which is not there in d time t1. And for the proof, we will demonstrate the existence of such a language. And just for the ease of explanation, right, we will just stick to some simple specific functions, because it's just simpler to explain. Let's say t2 is n squared and t1 is n, which is fine because n log n is little of n log n is little of n squared. So this is okay, right? It fits the requirements of the time hierarchy theorem, right? Right. So we'll show it for this n and n squared, and the proof is exactly the same. It's just that for simplicity, it's easy to explain, right? Okay, and the language L that we construct, that is in t time n squared but not in d time n, we will not explicitly give what language it is. Rather, we will construct a Turing machine, and we will say that the Turing machine accepts a certain language L. Whatever the language L that is accepted by the Turing machine will be we will construct a Turing machine D, and whatever is recognized by that Turing machine D will be the language L that is in n squared, d time n squared, but not in d time n, right? So what is D, right? So again, like I just said, for the diagonalization of the undecidability, this is very similar. So D again takes a description of a Turing machine M as the input, right? And then it computes the length of the description. Okay, so this is a description of a Turing machine M, right? This M with angular brackets. So let n be the length of the description. Now what we do is we simulate, again this is very similar. Earlier we said that M is ran on its own description. So now we are simulating M on its own description, and the simulation we run for n power 1.9 steps. Okay, n power 1.9 steps. Okay, so why n power 1.9? Because it is some number that is between n squared and n. Okay, so we simulate M on its own description for n power 1.9 steps of the simulation. Okay, so the total simulation will happen for n power 1.9 steps, right? That much time. This is the amount of time that we are willing to devote for the simulation. So in that much time, n power 1.9 steps, whatever happens, right? If M accepts its own description, we reject, D rejects. If M does not accept its own description, right? So there are three possibilities. M can accept its own description, M may reject its own description, and third possibility is that we run out of time because we are only doing this for a fixed number of steps. So if M does not accept, so if it rejects or does not accept its own description, then D accepts the description of M, right? So again there is a flipping happening. If M accepts M, D rejects. If M does not accept M, D accepts, right? So again the only thing here is that earlier we had a decider and then we flipped the output. Here we are doing a simulation. So this is the key part that is different. The step key difference. Right. Here we have a simulation that is a time bounded simulation, and then we flip the output. Okay, and now we claim that the language recognized by this machine, this Turing machine D, is in order n squared time, is recognizable in d time n squared but not in d time n. First part is easy. Why is it in d time n squared? This is easy because we run the simulation only up to n power 1.9 steps. So it is less than order n squared. So as simple as that, right? This is easy. Second part is the harder part. Why is it not contained in d time n? So again, just like earlier we proved the diagonalization, we'll use diagonalization to show that why this language recognized by this Turing machine D cannot be decided in time n. Let's see why. Suppose it was decidable in time n, d time n. Okay. Now suppose, so we know it runs in time n power 1.9. You mean that, I mean the Turing machine D runs in n power 1.9 time, and now we are saying that suppose it actually can be decided in order n time, d time n. So maybe there is another Turing machine that decides it in order n time. Let that Turing machine be called R. Okay. So this is R. R is a decider that decides the language decided by D in order n time. Now let us feed R as an input to the machine D. So now instead of earlier we fed D to its own description, we fed D its own description. So now we will feed D the description of R, and then we will see what ensues thereon, right? Right. So now we will feed R as an input to D, right? R or the description of it. So the key thing here is, if you may have noticed that the statement of time hierarchy theorem, there is a log thing happening here. Only when T1 is contained in T1 log T1 is little of T2 can we say this. Meaning if T1 is n and T2 is n log n, or let's say n square root of log n, then we cannot apply time hierarchy theorem, because T1 log T1 will be not little of T2. So this way it is not possible, right? So what I am saying is that we have this log requirement here. Why does the log requirement appear? The log requirement appears because how does the simulation happen? So how does one machine simulate another Turing machine? So earlier we used, in theory of computation course, you might have seen that we used to just say we simulate this machine on that machine and so on. But here we are bothered about the time, so we need to keep track of how much time it takes, right? So a Turing machine that runs in time Tn actually needs Tn log Tn time to be simulated. So right, it requires Tn log Tn time to be simulated by a universal Turing machine. So universal Turing machine is something that can simulate everything. Okay. So this is a result by Henny and Stearns from 1966. And basically a machine that runs in Tn time, for another machine to simulate the same thing, it takes Tn log Tn time. So for simulating one machine by another, the time increases logarithmically by a logarithmic factor. So this is the reason why we have a logarithmic factor in the statement of the time hierarchy theorem as well. If this was not there, then we would also need to have the log factor in the time hierarchy theorem. This log goes all the way to that log, right? So, and this is the best that we know. The Henny and Stearns result has not been improved from 66, right? So now how does it follow? So now again the goal here is, what we have now is a Turing machine D, and which runs in order n square time or n power 1.9 time. We assume that it has an order n decider, and that decider is called R, and now we are going to feed the description of R to D. Okay. Amongst all the descriptions, we pick a description X. Okay, so let n be the length of the description of X. So n is length of X. X is describing R, such that n is chosen such that, or X is chosen such that, so we said that, so obviously n power 1.9 is bigger than n log n, but we'll choose n such that, so maybe for small values of n, maybe the right hand side is bigger. So we'll choose n such that the left hand side, the asymptotics kick in. So maybe at the initial part, smaller values of n, it could be that the right hand side is bigger. So we'll choose beyond a point, the left hand side will be bigger. So we'll choose n like that. Okay. So now we run D on the description of R, or a specific description of R called X. Okay. Now what happens? So you are giving X as the input of D. So what does D do? It simulates R. So X. So notice that recall that X is a description of R. So D will simulate R on X for n power 1.9 steps, right? And R is assumed to be linear time, right? So by order n time, R would have decided either way. And even taking into account the logarithmic overhead required for the simulation, n log n is smaller than, and even n log n is smaller than n power 1.9. So we will certainly have known whether R accepts or R rejects. R not being able to decide and terminating will not happen, because we know that R terminates in order n time and we have accounted for enough time. So now D rejects X if R accepts, and D accepts X if R rejects. So now what does it mean? D and R were supposed to recognize the same language, right? So that's how we picked R. R was picked to be another machine which decides the same language as D in a smaller time. But now we are seeing in X that does not behave the same way in D and R. So whatever D does with R, whatever R does with X, D does the opposite. So this is a contradiction. L of D is not equal to L of R. Again, this is a diagonalization proof, and diagonalization proofs can be tricky. So let me just go over it once more. So D is the following machine. Given an input, which is a description of a Turing machine, it first computes the length of that input, right? So given M, it computes the length of M and simulate the machine on its own description, right? M is simulated on its own description for n power 1.9 steps, and D rejects if M accepts and D accepts if M does not accept. So basically flipping the output of M. And the language decided by D, we claim that it is in order n, it is in D time n squared, but not in D time n. Why so? It's in D time n squared because the simulation runs in n power 1.9 time, and it is not in D time n because we assume the opposite and arrive at a contradiction. So we assume that it is in D time n through a machine R. So R is a decider for D which runs in D time n, and now we feed a specific input, specific description of R called X to D, right? And this specific description is chosen such that the length of the description is n, and we can complete the simulation in n power 1.9 time. So okay. So now D, what does D do on when it takes X as input? X, recall that X is a description of R. So it will run R on its own, R on X, and then do the opposite. And we know that R will terminate the computation on X, and D will do the opposite. So by definition, D does the opposite of what R does on the same input. But then R was chosen to be, or R was decided to be, something that decides the same language as D. That's a contradiction, right? Just some. So this is the time hierarchy theorem. So why? What is hierarchical about time hierarchy theorem? So with this I can show that D time, we have already seen that D time n is contained in, but not. It is not equal to, meaning that the containment is strict in n squared. d time n squared is contained in d time n cubed, right? Anything, right? Maybe I can say even more things. D time and n squared is even contained in d time n squared square root of n, right? Because again you can work out it. So like that we can, so if there is significant gap between t1 and t2, then there is a language that that can be decided in t2 but not in t1. And these languages are usually, so you can see how non-explicit this is, right? We are not specifically telling which language it is, but we are saying that this is a language. Right. Now finally I will just conclude by saying what are time constructible functions, right? So the key point here is we should be able to compute t2n in t2n time, right? So here d here, sorry, d here simulates m on n power 1.9 steps, right? So this n power 1.9 it needs to compute. So is n power 1.9, so if n power 1.9 itself takes n cubed time to compute, then this, what we said here is not correct. N power 1.9, the value may be smaller, but to compute that takes n cubed time, then it is not in d time n squared, right? So we need to make sure that n power 1.9 can be computed in n power 1.9 time. And this is exactly what time constructibility is. T2, the function T2 should be computable in T2n time, and this is what is time constructibility. So more formally, a function T is called time constructible if we give a unary, n in unary as an input, meaning if we give n ones, right, a string of n ones as an input, and the to a Turing machine is called time constructible. Okay, maybe that's a small thing that I need to, sorry. Sorry, if there is a Turing machine that on input what does that do? That Turing machine on input 1 power n, meaning n ones, n in the unary system, it takes that as input and it outputs the binary, it computes tn, the function, in order tn steps. Basically we want to be able to compute a function whatever it is on in that much time. So example, almost everything, n squared, so n can be computed in n time, n squared computed in n squared time, 2 power n, log n. So you can, maybe you can try this. Why is this time constructible? You can think about this. These are all time constructible functions. In fact, most of whatever we can think of are time constructible functions. To demonstrate something that is not time constructible, we again need to resort to diagonalization and make highly artificial functions, right? That's about time constructibility. And finally, one more thing, I said that d time t1 is strictly contained in d time t2 if t1 log t1 is contained is little o of t2, right? And I said that there is no better simulation known, but there is a better simulation known due to Führer. If we fix the number of tapes, okay, so if we fix the number of tapes to k, then there is a better simulation known where and because of that we can get a strict hierarchy. D time t1 is contained, d time t2 strictly contained, contained but not equal to, whenever t1 is little o of t2. So Even in this case, like the one that I wrote here, okay, I've erased that probability. Even when T1 is n squared and T2 is n squared square root log n, even then this containment will work. But this is only when the number of tapes are fixed for both left hand side as well as right hand side, and not in general. So that is the time hierarchy theorem. So now, given any two functions like n squared and cubed and n squared and n cubed, which are sufficiently separated, then there is a language that can be computed in n cubed time but not in n squared time. That's the summary of this lecture. Again, diagonalization can be a bit confusing. Just keep rewatching it and thinking about it. I think after a while it will become clear, right? Okay, yeah, thank you.